Final seminar this semester. We're happy to have Bergshoeff from Groningen, and he's going to talk about applied Newton-Cartan geometry.
Okay, thanks for the introduction. It's a pleasure for me to give you a seminar. So indeed, what I will do is that I will give a talk on applied Newton-Cartan geometry. And Newton-Cartan geometry stands here for the geometry that represents non-relativistic gravity, so not general relativity. And so the first question to answer is why having general relativity to our position, we have it, why discuss non-relativistic gravity? Why should we go to the non-relativistic case? And I will give you three motivations of why there has been recently an increased interest in the structure of non-relativistic gravity. The first reason is that in these days gravity is not only used to describe the gravitational force, but it's also used as a tool to learn about quantum field theories. And it is via the well-known Holographic Principle, which makes a relationship between gravity in the bulk, often a gravity of an AES spacetime, and a quantum field theory that lives on the boundary of that bulk. And the point is now that we are certainly interested in quantum field theories in different dimensions, and both relativistic and non-relativistic, and that means that we're also interested in corresponding gravity theories, which are also then sometimes relativistic and sometimes non-relativistic. And the non-relativistic gravity theories have occurred in two disguises in studies of the holographic principle. One is in which people, they study non-relativistic holography, and they do it by still considering general relativity in the bulk, but they consider background solutions that have as isometries non-relativistic symmetries. So as for instance, the Lisic background, which is the Lisic isometries. That leads then to non-relativistic quantum field theories at the boundary, but these boundary field theories, as have been shown in recent work, they couple to Newton-Cartan gravity. So they are non-relativistic, so they don't couple to general relativity, but the Newton-Cartan geometry occurs at the boundary, and it occurs even in a way which was not known before. There's a certain extension which includes torsion, as I will explain today. And the other, less popular approach is that people also consider non-relativistic holography, but then they consider immediately in the bulk non-relativistic gravity. It's a kind of non-relativistic strings you consider. Then you get another type of non-relativistic quantum field theories at the boundary, which are invariant under different non-relativistic symmetries, but that approach is less under control and less well studied. But these are the two cases in which non-relativistic gravity occurs within the context of the holographic principle. Then the second motivation is recently people in condensed matter in quite independent way. They also started to study, they often work with effective field theories to describe condensed matter models, but they like to learn about properties of these effective field theories in general frames. And then you can learn something about genetic features. And there's a whole bunch of condensed matter people starting with the work by Son in 2005, who have studied quite a lot of these condensed matter models. The idea is a bit that in the same way as, let's say, if you only can learn about the Coriolis force if you work in a rotating frame. So if you work in more general frames, you learn more about genetic features. And in an effective field theory, working in a general frame means you have to couple to gravity. But since these effective field theories are often non-relativistic, they have to couple to non-relativistic gravity, or what we call Newton-Cartan gravity. And they have to learn also how to do it, how to couple, etc. And there's a lot of work where they try to take over a lot of techniques which have been developed in the relativistic case, like anomalies and all these things. They try to take over to the non-relativistic case, and they have not been worked out very completely so far. And then the second example is, I will shortly mention, and in this talk also, the supersymmetric extensions of non-relativistic gravity. And they are interesting in the sense that even in the relativistic case, people have developed powerful localization techniques to calculate exactly partition functions of supersymmetric field theories. And this has been done in quite a lot. There's a recently big review volume by people in the relativistic case. But of course, partition functions also exist for non-relativistic supersymmetric field theories. And in these studies, to get to know these supersymmetric field theories, to get them, there's a trick that's been developed by Verstucci and Seiberg, in which they use also relativistic supersymmetric gravity theories. So in extending this to the non-relativistic case, it's interesting to consider also supersymmetric extensions of Newton-Cartan gravity. And this has been done already in 3 dimensions, not yet in 4, and also to study more general obviously these gravity theories, because each time we have one, it can be useful to construct these supersymmetric field theories, and you can have new partition functions. And a general message I want to give in this talk is that although relativity is quite unique, we will see that in a certain sense, non-relativistic gravity theories are less unique. You can give more examples, not only Newton-Cartan gravity, but there are also other models of gravity. And they are interesting because they give you new ways to apply these gravity models to apply to the supersonic mobilization. And I will end this talk with giving you an example of a new gravity theory in 3 dimensions, different from Newton-Cartan. And it has the advantage that allows for solutions also with curved backgrounds, which are very hard to find in the case of the Newton-Cartan case, and they're certainly of interest if you want to consider these supersymmetric field theories. So these are 3 motivations, but before I start, what I would like to do in this talk is really give you 3 independent ways of constructing these Newton-Cartan gravity theories and their geometry, and I will show you also how to compare them. You'll see that the problem that an issue that arises in one approach comes back in the other approach. And that I will do first, and then after these 3 methods, I'll give you an example of a new gravity theory in 3 dimensions. So let me remind you of the first basic facts of non-relativistic gravity. So in the non-relativistic case, free-falling frames, they are connected by the Galilean symmetries, and Newtonian gravity has been developed by Newton in a special frame, and that is not a free-falling frame. That is a frame with constant acceleration, and that's an Earth-based frame. A frame fixed to the surface of the Earth cannot fall down, so it's a constant acceleration with respect to free fall, and it is non-rotating. That's what I call an Earth-based frame. And then we have the well-known law of Newtonian gravity, and for that we need to describe gravity in that frame. We need a Newton potential. But interestingly enough, although you can calculate Newton's laws also in a rotating frame and all kinds of frames, Newton never gave a formulation independent of a frame independent formulation. And the reason that he didn't do that is that in order to do that, you need a branch of mathematics which was not yet quite developed in these days. Because we know now that you need geometry. So for a frame independent formulation, you need geometry. And geometry was only developed in the middle of the 19th century by Riemann. It's a simple question to ask. Every law of physics should be independent of the frame. If you ask you how to do that, that is then not so easy. Now, in effect, you could say Einstein really achieved 100 years ago, when he developed his theory of relativity, he did 2 important things. One is that he made his theory of gravity consistent with special relativity. He didn't like the action on the distance of Newton, so he introduced his theory of special relativity and made his gravity theory consistent with special relativity. But at the same time, also to realize the principle of equivalence, he made it into a frame-independent formulation. And again, he needed for that geometry. And we all know that that relativity now, first of all, so to get to make it consistent with special relativity, free-falling frames are now connected by the Poincare symmetries, which are different from the Galilean symmetries. And to formulate an arbitrary frame, you need not a Newton potential, but you need the metric tensor. It had a geometric interpretation. It was the metric of an underlying Riemannian geometry. But once you've done that, of course, anybody at that time could have asked yourself the question, well, let's go back to Newton, because now we learned from Einstein, you need geometry and this metric, etc., to describe geometry in the arbitrary frame. Can I now, for a moment, forget about special relativity, but can I also reformulate Newton in the arbitrary frame? And what's then the corresponding geometry? And that was done only 8 years later by Cartan, and that's why it's called Newton-Cartan gravity. So he reformulated the laws of Newton in an arbitrary frame. But the rule is that if you ignore source terms, that in some sense, if you want to formulate gravity in an arbitrary frame, you have more symmetries, but at the same time you need more fields. So you need more gravitational fields than the Newton potential. And I will show you in a minute which kinds of fields we need. And then it's really a kind of gauge, it's equivalent to the original rule of Newton, because if you want to go back to special frames, what you do is do gauge fixing. You impose constraints on these extra gravitational fields, you have less symmetries, and then you can either go back to an Earth-based frame, where you have the Newton potential left, or even to free-falling frames, where there is no gravity left. It's all a matter of more frames, you need more gravitational fields, more restricted frames, less gravitational fields. And he showed you how to do that. And the geometry that you need, you can compare in some sense with a Dutch bread, in the sense of the difference with the Riemannian geometry of Einstein is that you have a foliation, it's an absolute time. So in other words, it's a kind of a bread with slices, so the universe is, let's say, this universe at t is 0, this universe at t is 1, and second t is 2 seconds. So if you have 2 events, that it's very clear if the two events are in the same slice of bread, then they happen simultaneously. If they happen in two slices of bread, two different slices of bread, they didn't happen simultaneously. And the difference with Riemannian geometry in some sense is the product before slicing. So you decide how to slice it. You can slice it in this way, but you could also slice it in diagonal slices. And that's why if you have two events in this bread, you can't say that they happen at the same time or not, because it depends on the way you slice the bread. That's the way how you find time. That's why time is relative in the relativity and it's absolute in the Newtonian approach. And that's because of this foliation. So that's an important ingredient of the Newton-Cartan geometry. Now, are there any questions at this point? Because now I want to say what I'm going to do in this talk, and this was just the introduction. So what I'm going to do in this talk is I'm going to tell you in three different ways how to construct this so-called theory of Newton-Cartan gravity. First, I will do it by a so-called gauging procedure. I will gauge a certain symmetry algebra. Then I will do it by a procedure which is called null-reduction. I will start from general relativity in 5 space-time dimensions and I will perform a kind of null-reduction and obtain Newton-Cartan gravity in 4 dimensions. And thirdly, I will do it by taking limits, by taking non-relativistic limits. This sounds like very easy. What can be easier than taking the non-relativistic limit? We'll see it's more subtle than you think. So let's be careful. The limit is also not unique. And having introduced these 3 methods and comparing them, at the end of the talk I will discuss extensions and I will give you an example of a kind of new gravity theory in 3 dimensions, which could be interesting from the point of view of, for instance, condensed matter applications. And then conclusions, further developments.
So this non-reduction wasn't kind of age fixing? Or?
I'm going to discuss it, so I will come back to it, because these are the things I'm going to do. So first the gauging. So we all know that Einstein gravity free-falling frames are connected by Poincare symmetries. So these are the space-time translations and the Lorentz transformations. And in our 2 frames, the gravitational force is described by metric, I told you, but I will work here instead with an invertible V-by metric. And that's really equivalent to the metric. You always can construct a metric out of the product of 2 V-bys. But I like the V-by formulation because that looks more like a gauge field. And I'm going to gauge a symmetry, then you work with gauge fields. So it's really easy to not think about the metric and only work in terms of this V-by. Then mu is here the curved index and A is the Lorentz index of these Lorentz transformations. And we all know, or at least some of you know, that the kinematics, the symmetries of Einstein gravity, the way how this V-by transforms, can be obtained from quote-unquote a kind of gauging procedure of the Poincare algebra, similar but not quite the same as if you gauge this Mills algebra. And what I would like to do now is do the same procedure in more detail for the non-relativistic case. But there are some issues arises. So first of all, we all know that in the non-relativistic case, I already told you that free-falling frames are connected by the Galilean symmetries, which I split now translations in time and space, and the rotators are split in spatial rotators and the Galilean boosts. Now, these are the same number of symmetries as the Poincare symmetries in the relativistic case. The difference is in the Galilean boosts. Because in the Galilean boost only transform space into time, whereas the relativistic boosts also transform time and space. But since time is absolute, I don't do that. So you have the same number of symmetries, but the boosts are different. That's why I call it Galilean boost. And that makes an important difference. Now, I should also tell you that, so what I will call Newtonian gravity, that's the original description of gravity by Newton, in a frame with constant acceleration, in an Earth-based frame. And we know that then we need just a Newton potential. And I told you that if you need more frames, you need more gravitational fields. And what Cartan found is that if you really want to describe this non-relativistic gravity in an arbitrary frame, then you need the following fields. First of all, you need 2 fields which you can call a temporal V-by and a spatial V-by, where A is now a spatial index only. And in some sense, you could say that this is the kind of, this is together, there's as many fields as the relativistic V-by. This is kind of the time direction, if the Lorentz index is in the time and the Lorentz index is in the space direction. So the number of fields doesn't change. The only difference is that in the relativistic case, these 2 guys always go together because you have Lorentz symmetry. Whereas in the non-relativistic case, I only have spatial rotation boost and I can use them independently. So if they always occur as if you decompose a relativistic V-by, then I have relativistic gravity, but I use them independently. Now, more or less it makes sense that that's what you need, but the surprise now is that it turns out that that's not enough information. You also need a vector field. And there are several reasons to expect that indeed you need an extra vector field, and I will give you several reasons in the talk to come. So it's a bit strange, you think, well, you this tau and E is reasonable, but why is it a vector field? But we will see why. I will give you immediately now already one reason. So the point is that, you see, we know that the contraction, the non-relativistic contraction of Poincare algebra is the Galilei algebra. So if you get Einstein by gauging Poincare, you would think I get Newton-Cartan by gauging the Galilei algebra. But that's not true. What you need is a kind of Galilei algebra with a central extension. And that's called the Bartman algebra. Now why is that? That's for some sense the surprise. That you can already see from just by looking to compare mass of particles. So the argument only applies if there is a mass in the game. If there is no mass in the game, then the story goes slightly different, and I will say more about it later. Because you see, if you compare a relativistic versus a non-relativistic mass of particle, then the action of a relativistic particle is manifestly invariant in Poincare symmetries. I have just this contraction of the curved indices. But the action of a non-relativistic particle is given by this term here, where xi are the three Latin coordinates for the spatial directions. And tau is the evolution parameter, and t is the time. And it turns out this standard action is not, the Lagrangian is not invariant in the Galilean boost. Instead, the Lagrangian transforms the total derivative. Remember, the x went to a lambda t and the boost, so x dot goes to lambda. For a constant Galilean boost, this becomes then a total derivative. It's this term. And in principle, it's okay, because the only thing we want is that the action is invariant in the Galilean boost. But what it means is that the definition of neutral charges gets changed. It's well known that if a Lagrangian is not invariant with the action, then you have to modify the definition of the neutral charges, and that always leads to a central extension in the corresponding algebra of neutral charges. And the same thing happens here, and that gives you exactly the central charge in the Galilei algebra, which promotes it to a Bartman algebra. Now, and that's why we gauge the Bartman algebra, and we will see in a minute also why we need the central extension. So I've written here the Galilei algebra, so the J are spatial rotations, P spatial translations, H time translations, and then I have the Galilean boost and spatial rotations, and Z is this extra central charge transformation. So it is a central charge. So it occurs in the commutator of a Galilean boost and a spatial translation. And engaging it, first of all, I do the standard procedure to every symmetry I have. So a generator, I introduce a gauge field, I have here, and a curvature, which transform covariantly under the symmetries. And here already you see the tau and the E, which will become the time-like and spatial vierbein of Newton-Cartan gravity. Here we see the vector field of central charge, and here we see two fields which are the analogs of the spin connection field of generativity. But we know from generativity that these spin connection fields are not independent, they are dependent. And if I want to mimic that, it's not inconsistent, even in spin connection is independent, but since I want to have something that has to do with generativity, I would like them to be dependent. And the way to make them dependent is that I'm going to impose constraints on these curvatures. That gives me algebraic relations which enables me to solve the spin connections. That's how it goes in generativity. But here is a problem. The problem is that, you see, what you do in generativity, you set the torsion equal to 0. You set the curvature corresponding to the vierbein equal to 0. But here, I only set the curvature corresponding to the spatial vierbein to 0. Because the curvature corresponding to the time-like vierbein I've given here, that doesn't contain omega. Because remember, that was the difference between the boost. The Galilean boosts have one structure constant less, and that's exactly the one which in relativity gives you an omega. So in the relativistic case, you set this curvature and this curvature to 0, it enables you to solve the spin connections. But in the non-relativistic case, I can't use this because there is no omega. So if I don't do anything, for the Galilei algebra, I could not solve for the spin connections. But now the central charge comes to help, because it turns out that the curvature of central charge transformation does contain the spin connection field. And that helps you to solve for the spin connection fields in terms of the other fields. So that, without the central charge, I could not do that. Nevertheless, I still impose this curvature of the time translations to 0, and that's the foliation condition. It's a condition I impose by hand because I want to foliate the geometry. So the curl of tau 0 tells you tau is the drift of a function tau, and usually take for tau t, and it tells you that specifies the time direction. That's slicing the breadth. And then the curvatures for spatial rotation Galilean boost, you don't impose constraints just if you do only kinematics. And if you do that, then you get just the transformation rules of Newton-Cartan gravity. So the independent fields are now this time and spatial vierbein, this extra central charge transformation, and they transform as covariant vectors under general coordinate transformations, and under spatial rotations and Galilean boost, they transform in this way. And the spin connection fields are now dependent, but note that they are expressed not only in terms of E and tau, but also in terms of this M. So it's not possible to, if you would require expressions for omega and omega which behave like gauge fields, you will not be able to do it with only E and tau, like in general relativity, where the V-bar is enough. Then you have the spin connection transforms and Lorentz transformations. Here something goes wrong with the Galilean boosts, and to correct for it, you have to add extra terms M, and you see that exactly gets these boost terms, which enables you to cancel the complementary terms. So you really need all three fields to make the expressions which transform its function as the gauge fields of spatial rotation Galilean boost. Yes?
How does that, is that still make, I mean, previously I had a condition on M that M was flat, right?
That M was, the curvature of M was 0, yeah.
Right, so is that still true now that when you do this transformation?
Yeah, but remember the curvature of M, that was a trick, is not only the curl of M, but it also contains an omega E term. So in other words, I use it to solve for omega. So after I've solved it for omega, that's why omega depends on M, there is no constraint on M. So M itself does not satisfy any constraint. I've solved this curvature constraint. So all curvature constraints I impose, I've solved for, I've used to solve for omega. So they are gone. There are no, these fields here are unconstrained. Now, once you have that, so I have now the symmetries in a general frame, you almost can go back to special frames, as I said, by gauge fixing. So for instance, in the extreme case, suppose I want to go back from general frames to free-falling frames, I gauge fix all the gravitational fields I have, I set them to 1 or to 0, and using the transformations I just gave you, you require the gauge fixing to be independent and the symmetry should be preserved. You get just the following non-relativistic Killing equations, certain differential equations, and if you solve it, you get exactly the recovered Galilean symmetries. But, yeah.
The first one, the choice.
What?
I mean, the first one, so previously tau, you want to be able to have tau equal to T in some.
That's a gauge fixing condition.
Yeah.
I say, I impose you, because I go to special frames,
Yeah.
I go to frames where tau is a constant.
Would it also be possible to pick some spatial vector and set tau equal to that vector dotted with X?
You can impose many gauge fixing conditions, as long as you fix the gauge. That's what you need. So, let me finish this. This is just the gauge fixing in which I go to free-falling frames. And I know that in free-falling frames I don't need gravitational fields. And then you are left with the Galilean symmetries. But for instance, I could say, I want some more. I want not only free-falling frames, but also Earth-based frames. Then you have to impose less, you have less gauge fixing conditions, and you get more symmetries. And then what happens is that one component is here not 0, and that's exactly the Newton potential. For instance, the Newton potential is hidden in the time component of MU, so that you don't sit at 0. Then you have more symmetries, and if you look to the Newton-Cartan equation of motions, the Poisson equation of the Newton potential, it's invariant under more than the Galilean symmetries. It's so-called acceleration extended Galilean symmetries, in which the boost is a function of time. So it's more. So you have more frames and more symmetries and more gravitational fields. And if I said, then I could gauge fix even the Newton potential, I could set it to 1. That would fix me from acceleration extended Galilean to normal Galilean and the free-falling frame. So they're all equivalent formulations, if you ignore source terms.
Yeah, just a question. In these free-falling frames, just make sure I understand.
What?
In these free-falling frames, the curvature tensors all vanish, right?
Yeah.
Okay.
Yeah.
Okay, just making sure.
Now, so this was the kinematics.
Well, not exactly vanishing. Here's what you have here. Is big version of it is vanishing.
Well,
Not all of them are vanishing curvatures.
No.
It will be empty of dynamics. Your new
no,
slide.
our gauge fixing condition also has to be consistent with the equations of motions, of course.
Yeah, but setting the curvatures to 0, all curvatures, is too strong.
That's what curvature should I have?
If you go to the next page,
Well,
the one you showed just flashed, go next.
But be careful. If I have Newton gravity, I have non-zero curvatures, because we know that you can rewrite the Poisson equation as a curvature in the space-time component. So then I have a curvature. But I was talking about the free-falling frames.
Oh, okay. In the free-falling case.
But in Newton gravity, then you have curvature.
Okay.
You know that. Now, so this I impose by hand. I impose now also curvatures or constraints on the Galilean boost and the spatial curvatures. And I impose here a singlet. It's a kind of time-space component of this curvature. It's a singlet. And here this has a free index, a curved index, and a spatial index. If the curved index is time, it's like a vector with spatial rotations. If the curvature is spatial, it's a kind of symmetric tensor. And this is exactly also the decomposition if you take the Einstein equation of general relativity and decompose them in time and space. So what I want to say is that I impose the same number of equations as in general relativity, but they are now constrained on these non-relativistic curvatures. If you again put gates fixing to Earth-based frames and you assume flat space, then this first equation exactly becomes the Poisson equation of the Newton potential. So that's really hidden in that equation. It's just this is the frame-independent formulation in that sense of the Poisson equation of Newton. What is not the case is that given this formulation, it is not possible, at least I've never seen it, to write down an action that gives rise to these equations of motion. So you don't have the analog of an Einstein-Hilbert action. And you'll see several reasons in a minute, each time confirming this statement, that there is no action for Newton-Cartan gravity. At least you can never say there's no action, because maybe I think there's more fields using, because I'm not making a no-go theorem, but given these fields, there is no action. One problem also which you have is that, for instance, in general relativity, you see the equations of motions are a symmetric tensor, and the basic variable is also a symmetric tensor. You need as many fields as equations of motions, but here there's no maximum, because you have these three fields, E, tau, mu, they don't quite add up to these equations of motion. But there are several reasons why you see there is no action. So we will come back to that.
Eric, I'm just confused.
What?
The field line is rectangular, right?
If you may.
The field line is rectangular.
Yeah, 4 by 3. Yeah.
Right, so
Yeah,
I'm
it's
just
spatial
curious.
field line, yeah.
I'm just a little bit confused with the inverse field line.
Well, I didn't tell you. I defined, of course, a projective inverse of the field line. Basically, what it is it is really the same invertibility relations of the general relativity, where you have split in space and time, but it involves also the tau. So it's not just it's a 4 by 3.
It's 4 by 4 and then
yeah. I had not defined. Sorry, I had not defined the inverse, but. Now, that was the gating. So I have the kinematics, I impose equation motion by hand, there is no action. Is there any question at this point? Because now we do the second method, the null-reduction. Yeah.
What fixes that the gradient of tau is time by?
No, well, that's a good point. That you have to impose by hand, because we like a time developed, we want absolute time. But I will tell you that in the condensed matter community, they don't do that. They could like us to consider Newton-Cartan geometry with arbitrary torsion, as they call it. And the reason is that, you see, they're not interested in dynamic gravity, but they're interested in coupling effective field theory to gravity. So they are less flexible, more flexible causality, etc. And the reason that they don't like this constraint, because tau is time translations that corresponds to the need to the coupling to define the energy current of a condensed matter system. But if the gate is constrained, it's very hard to define the energy current. So they have some trick where they temporarily give up this constraint, they calculate the energy current, and at the very end of the calculation, somehow there's a technique for that. They still impose it, but they like to work more with a formulation where they do not impose a constraint. But of course, from the gravity point of view, if you don't impose a constraint, you get pulled with causality, etc. It's very, he would like to impose for the theory of gravity, he would like to impose it. But you have to impose it by hand. It doesn't follow from the gate, you're not forced to do it. Now the null-reduction. So let me first briefly remind you what the standard reduction is. If you can standard reduce 5-dimensional relativity to 4-dimensional relativity by what's called the Cauchy-Klein reduction. So you take the 5 coordinates, you split it in 4, and let's say a circle coordinate, and then the curved indexes you split in u and in x and y. You give the dot to indicate it's curved, and the Lorentz index also in a 4-dimensional Lorentz in y, and then you shoot a non-null killing vector, it's the direction of the circle. And if you truncate, you would say I ignore all Cauchy-Klein modes, I set the derivative with respect to the circle direction of all fields to 0. And then you impose a reduction ansatz in which the 5-dimensional Fünfbein you parameterize in terms of a 4-dimensional Vierbein, and Cauchy-Klein vector, and the dilaton, and Cauchy-Klein scalar. And note, this is the most general parameterization. The fact that this is 0 has to do with gates fixing, because you see, I'm only interested in 4-dimensional Lorentz transformation, but I'm not interested in Lorentz rotation that brings you from the 4th to the 5th direction. So I gates fix that Lorentz transformation by setting this to 0. And then you get general, if you plug this in the 5-dimensional Einstein-Hilbert action, you get 4-dimensional Einstein general relativity coupled to a scalar and vector, and you can consistently set it to 0, truncate them, and make it Einstein gravity. That's standard reduction. You go from general relativity to general relativity. Now, what I do is I do a null reduction. And what I do now is that I pick out two null directions in 5 dimensions, u and v. And the v plays the role of the extra direction, and the u plays the role of the time direction within x mu, but you never have to indicate it explicitly. And the curved indices, I split that in mu and v, but I do it differently for the Lorentz indices. That I split to a spatial index and the plus and min null directions. And I assume now the existence of a null killing vector, so that's the v, but now comes the important point, that imposes a constraint on the metric, because you see, if you want the null means the length squared is 0, and if the mu is in the v direction, it means that the vv component of the metric is 0. So, in other words, you don't do the most general parameterization, you also set one component of the metric to 0, but then, if you do that, you're not allowed anymore to substitute this in the 5-dimensional Einstein-Unit, because then you lose information. You lose the information about the equation of motion of this extra Kutzke-Klein scalar. So that's why you can only do this in the equations of motion, and then you get an answer, but you don't get an answer for the Newton-Cartan gravity. And we know that that action we think doesn't exist. So I do now the reduction action only on the equations of motion, and then so m are decomposed in 4 plus 1, and the Lorentz index in 3 plus 1 plus 1. And here I put exactly these 3 vectors of Newton-Cartan. Is E mu A, the time, tau is kind of the time component of the spatial v line, and m is like the separate charge vectors, translations in 1 dimension higher. And now the 0 and the 1 here is again gates fixing, because I have now 5-dimensional Lorentz rotations, but the only thing I want to know in Newton-Cartan gravity is spatial pace and Galilean boost. So there is a lambda A plus and a lambda plus minus, which have gates fixed, and that leads to this 0 and 1. But then this thing here, that's also a constraint. I put this to 0 really because of this null killing vector. And now I can substitute this in the equations of motions and in the transformation rules. And believe me, if you do that consistently, you get exactly the transformation rules of Newton-Cartan gravity and the equations of motions of Newton-Cartan gravity. Now, the point is only what you don't get out of this method is a constraint on the torsion, because as I said, torsion you have to impose by hand, and general relativity didn't know about foliation. So if you just do this now in, let's say, in the transformations, the kinematics, then you get a version of Newton-Cartan gravity with arbitrary torsion. And as I said, I imposed it by hand because I wanted to have an absolute time. But really, in this gating procedure, there was no need to do that. If you don't do that, you can still solve for the spin connections, but they get now extra modifications with distortion. So the spin connections can still be solved for, or they boost, but they get extra contributions to torsion. Now, when Julian Nicolai did this work many years ago, they also substituted this in equations of motions, and they didn't know about Newton-Cartan torsion, they only knew about Newton-Cartan zero torsion. And then what they did is they substituted this in equations of motions, and if you do that, because there are more equations of motion in 5 than in 4, they got extra constraints on distortion, one an algebraic condition and one differential equation, and then if you impose proper boundary conditions, they got zero torsion. But that's not so nice, because if you do that, then the result is very action dependent, because if you add matter, for instance, to the relativity, you get different equations of motion. So it's much nicer as a way to obtain non-relativistic answers to do this off-shell. You get exactly the dynamics, but with arbitrary torsion, and then you can always truncate if you want. You have arbitrary torsion, I can set torsion to 0. That is a consistent truncation. Yeah? And you also have another possibility, which you miss in this case, and that's something in between non-zero torsion and zero torsion. That's called twistless torsion. And that is the case that arises, for instance, in Lipschitz holography, that arises in the conformal context. If you have conformal field theories, you see in some sense it's inconsistent to set the torsion to 0 because that's not covariant in the dilatations. So you have to do it more mildly. And the outcome is, and I will show you now in a minute, is that you get twistless torsion. That's consistent with dilatations. And that's what people find in Lipschitz holography. They find Newton-Cartan geometry with twistless torsion. And one way to see this
in what dimension is that?
What?
In what dimension?
Any is in dimension independent. This twistless torsion.
Conformally invariant.
What?
Any dimension? Conformally invariant.
Well, to make, yeah, because if you want to make this conformal invariant, you add just dilatation case field, but then you get a b tau, that's always 0 tau is antisymmetry. So this is a dimension independent thing.
Okay.
But let me, because to show you, it's also interesting to do that in the conformal case. So suppose now, because what I did is I did in some sense general relativity, Poincare gravity. Just looking at the kinematics, I reduced from 5 to 4. But let's now take conformal gravity, because then I have an extra rule, namely dilatations. The dilatation for conformal gravity is that the Fünfbein, that for 5 to 4, has a certain scale. But it's clearly isotropic, it's always the same scale. The funny thing is now that if you do this reduction for 5 to 4 over a null direction, then it becomes an anisotropic scale. In other words, the spatial vierbein and the time-like vierbein, they transform with different weights. We call it also a dynamical exponent, Z is 2. And we think, how can it be, if this is isotropic and if you reduce, how can this become anisotropic? The reason is that, remember when I did the reduction, I did some gauge fixing. And I set some scale is equal to 0. And if you reduce, what you get is not just E and tau, but multiplied by certain scalars. And they also transform into dilatations. And if you set these scales to 1, you get compensating transformations. And if you work out the details, at the end of the day, you will find that E and tau transform, the tau transforms twice as hard as E if you use null reduction. And in fact, what you get is what is known as the gauge theory of, it's not a kind of conformal gravity, but what's called Schrödinger gravity. So you get the gauge theory of the Schrödinger algebra with arbitrary torsion. And that's what is found in this Richards field theories. And so what is, in some sense, what is Schrödinger, the Schrödinger algebra? That's the following. So you have relativistically, you have the Poincare algebra, you have the conformal algebra. But if you take the truncation of Poincare, you get Galilean. If you take the truncation of conformal, you get Galilean conformal. But Galilean conformal is not so nice. That doesn't allow a central extension. It's too much conformal symmetry. And the nice thing of the Schrödinger algebra, it's something in between conformal and Poincare. It has less symmetries, but it allows a central extension. And that's what you need in this Newton-Cartan context. You have a mass parameter. So that's why the Schrödinger algebra arises naturally in this context. It's kind of, well, conformal in the sense that there's dilatations, but it's also not conformal in the sense that it allows a mass parameter, it allows a central extension. And that's what arises from this null reduction. And the way it really arises if you gauge the Schrödinger algebra is that the curvature of time translations is now not anymore d tau is 0, but it is the covariant derivative of tau is 0 with b mu. And what happens now is that you see the time component of b mu doesn't occur, it's only the spatial component. Now the time component of the b, that is a kind of Stuckelberg variable, because there is also a corresponding special conformal transformation. So it's really not there. But the spatial component, and that's different from the relativistic case, this now has become a conventional constraint. This equation can now be used to solve for the spatial part of the dilatation gauge field. So the dilatation gauge field, unlike in the relativistic case, has like spin connection fields become dependent. It's just this one. And if you substitute that back here, then you feel that the curl of tau is not 0, but it's exactly this expression. That's what we call twistless torsion. So twistless torsion is something very natural that arises in the context of the non-relativistic conformal field theories. And as I said, the Galilean conformal algebra doesn't play a role in this story because that doesn't allow central extensions and that has not yet a clear relationship with this whole Newton-Cartan business. So, in some sense, you could say, for many purposes, the conformal algebra in the relativistic case, its role is taken over by the Schrödinger algebra, by the Z is 2 Schrödinger algebra in the non-relativistic case. It has to be Z is 2. Because that's the only one which allows for special conformal transformations. If you have Z is not equal to, then you get different kind of Schrödinger algebras which are not, they're less easier to use here. That is the null reduction. Is there anything about that? Because the next thing I will do is the limits.
Physically speaking,
Yeah.
now you've given us 2 theories in 4-dimension, 2 gravity theories.
No.
Non-relativistic. What's the difference?
The difference is just torsion.
But is that more degree of freedom? Or?
No, it's just a torsion. It's just a deformation.
Just torsion.
It's a deformation.
Deformation.
No different field. So the leading part is the same. It's a deformation, I would say. You have arc
no
torsion.
spin degree of freedom.
What?
Is there still spin to still gravitational field?
Yeah, the same fields and the leading parts are the same. Thing. It's just literally I added torsion deformation. To
Okay, okay.
Now the limits. Now, at the level of the algebra, it's very clear what you do if you go to non-relativistic case. You do an inelitic contraction. So, and we know that the Poincare algebra, if you do it, you get the Galilean algebra. But I don't want the Galilean algebra because we just argued that we want the Barton algebra, which has an extra central extension. But that's one generator more. How can I get from Poincare if doing contraction, how can I get one generator more? I have to do something. And the trick is that, and that's very funny, is you add now an extra U1 generator which commutes with all these generators. There's nothing to do with these generators. But then I do a modified contraction. So the contraction amounts to, at the left I have the relativistic generators, and I express that in terms of what will become the non-relativistic generators with a parameter omega. And this you substitute in the relativistic algebra, and at the end of the day you take the limit omega to infinity. And then a certain structure constants vanish, and you get then a non-relativistic algebra. If you do it without this extra terms here, the z's, then you do a standard reduction of the Poincare and you get the Galilei algebra. But once you have this z here, I can do this trick. I can take the sum and differences and I take it in a clever way. And then what happens, and believe me or not, but if you do this algorithm I just told you, because in that calculation occurs once in a while 1 over omega now multiplied by an omega, and then it doesn't cancel anymore, and you get a surviving term which exactly is the center extension in the commutator of a boost and a translation.
But dynamically speaking, if you introduce z, even at the level of equations of motion, you don't have Einstein equation anymore to deal with.
Well,
you introduce a new dimension or what?
no, but I will come back to
Yeah.
it. But I'm not going to introduce a new degree of freedom.
New dimension.
New dimension.
Well, you introduce
No, this is, well, let's see, I will, because this is at the level of the algebra, I'm going to do it, what you say, in a minute. So, the point is now, I have gatings, contractions, and I want to define non-relativistic limits. So, Poincare, I told you, I need an extra U1. If I then do a contraction, I get Bergman. I explained the gating of Bergman, given Newton-Cartan. Now, it's clear that if you gate Poincare times U1, what you get, in some sense, is generativity, to which I add an extra vector field. But I don't want, I set its curvature to 0. I don't want a new degree of freedom. So I take a vector field with a curvature equal to 0. And then I try to mimic this contraction of the algebra, and the challenge is to find now the non-relativistic limit, which gives you Newton-Cartan gravity. It's good to have an extra vector, because I know that the Newton-Cartan gravity also has this extra vector. So if I...
So the equations are Einstein equation and the separate vanishing F mu nu 0 equation.
Yeah.
That's it.
Yeah.
Okay.
And in hindsight, we'll see that it plays an important role, this vector field, in defining limits if you couple to matter. Because, and then in fact, the role of this vector field is that it couples to the current, which expresses the conservation of particles minus antiparticles. So it's a very important vector if you couple to matter and you take the limits. Without the vector, you get these nonsensical answers. So, but now I take the limit for the moment only on gravity, and I want to define what I call the mass of non-relativistic limit. This is only important if you have a mass. So I add a vector, as I just said, to generativity with its curl to 0. And in step 1, I'm going to now mimic the contraction of the algebra. So whatever I did for the generators, I'm going to do for the Gates fields, but in a kind of opposite way, because I want that generator is correlated to a Gates field. But basically, it's the weakening linear contraction for all the Gates fields I'm going to do. But it's slightly, I mean, the point is that the limits here are much more subtle than in the algebra. The algebra is well defined. But here, for instance, one thing I have to deal with is that my vierbein is invertible. So if I scale my vierbein like this, I get an infinite expansion with the inverse vierbein. Also, some of my gate fields have become dependent. So you have to be very careful how you define whether things don't blow up. But if you do it in the right way, you do the scaling and form the right prescription, then what you find is that if you substitute this, for instance, in the equations of motions or in the transformations, and you take the limit omega to infinity, you exactly discover the transformations of Newton-Cartan gravity and the equations of motions of Newton-Cartan gravity. And again, if you try to do the same thing in the Einstein limit action, the answer blows up. It just doesn't work. So it doesn't lead to a finite action. Now, I must say, in some sense, this is really, if I ever had to write a textbook on generativity, then most people, if they discuss the non-relativistic case, they only give the Newtonian limit. But pedagogically, that's really not nice, because you see there are two issues. One is taking a non-relativistic limit, and the other is going to a special frame. And you should keep these two operations separately. So here, I only discuss the non-relativistic limit, but I state in an arbitrary frame. Now, if I want, I can go to a special frame. Whereas in this Newtonian limit, you immediately go both non-relativistic and you go to an Earth-based frame. And that's, in some sense, very confusing. So it's much nicer to do it in this way. Now, yeah, I should say that there are also other limits possible. The limit I just discussed made use of an extra vector. I call it the massive non-relativistic limit. And it has I have no time to discuss the coupling to matter, but if you add an extra scaling field, propagating scalar field and couple it to gravity, so in Klein-Gordon scalar coupled to gravity, and perform the limit I just described, it automatically becomes a Schrödinger action. But the important thing of the Schrödinger action is that the Schrödinger action has both a term of the time derivative and a term of the spatial derivative. And there's one time derivative, two spatial derivatives. And if you follow, but in this procedure, I should also say, this vector field you have to couple. So I have to take a complex scalar because I want my vector field transformed under the U1 of the vector field. And the U1 that couples really to the mass, it really couples to the, as I said, it's the current of particles minus antiparticles. If you do it in that way, you write really the thing with covalently coupled to this vector field, then you really get the Schrödinger action. If you would not introduce this vector field, and I call this the Galilei limit, you could do it, but then you could not, for instance, engaging the Galilei algebra, you could not solve for all spin connection fields. But that's okay in some sense, that's not inconsistent, it just means you get another geometry with independent spin connection fields. But if you would couple that to matter and then take the limit, the Galilei limit, then what happens is that and that's why this vector field is so important, you don't get now two terms with a time derivative and a spatial derivative, but one of them gets zero. So you get only a term with a spatial derivative. And there's also an opposite thing, you take what some of these people call the Carroll limit, it's the ultra-relativistic limit, and also not introducing vector, then you get only the time derivative. So this vector field is really very important with limit to get really a Schrödinger action, which is dynamic, and it's really a time derivative and a spatial derivative.
Eric, how can you have massless non-relativistic object?
Well, I call it massless because I don't introduce a mass parameter. That's why I call it. So I do not introduce a mass parameter, like I do at the moment I introduce a central extension. That is a mass parameter.
Yeah, but,
so that's what I mean.
But there must be somewhere that plays the role of mass.
No, I can take a limit. Let's say. Well, when I took this limit here.
I mean, if I go to Earth-based
limit
frame,
here, I could just not introduce this m and nevertheless take the limit. That's what I would call the Galilei limit. So I don't introduce this m, and I just do the scaling according to if I contract the Poincare algebra to the Galilei algebra.
But suppose I go to what you call Earth-based frame, f is equal to ma, no? How can m be 0?
To get, as I said, there are several limits, but if you want to get standard Newtonian gravity, I have to take the one with the vector field. Otherwise, I don't get. That's the one I get, which is the gravity which we know as given by Newton. I'm just saying this is an other limit where things don't blow up. You get some answer with, let's say, with invariant and diffeomorphisms, and this is Galilean invariance. So it depends on what you mean by gravity. If you mean gravity, really the gravitational force as we know it in this universe, you have to take this with a vector field with Newton-Cartan limit. But if you say I'm only interested in theory, which is invariant in the diffeomorphisms and is invariant in the Galilei symmetries, then there are more possibilities. And then you can take also this Galilei limit or the Carroll limit. They have all these symmetries. And they play a role in if you apply gravity as a tool, not to describe the gravity of our real world. You look like
We'll discuss later.
okay, we can discuss later. And this Carroll symmetry occurs, for instance, in recent discussions of flat space holography and warp CFT, which I will not get into. But so what I want to stress is, from the gravitational force point of view, this sounds like strange limits, but in recent theoretical investigations, they do occur as special corners in certain theories which have these symmetries. Now, I have 10 minutes, is that correct?
Yes.
Yeah.
Then I want to discuss extensions. So I want to discuss in some sense, we are writing a paper now in which we try to also gauge the Galilei algebra, so not introducing its central extension and the opposite, the Carroll algebra, and that leads to notions of Carroll and Galilei gravity. The nice thing is that these limits, by the way, you can take them in the Einstein-Hilbert action. So you get now really also theories which have an action. And then the funny thing is that the components of the spin connection you cannot solve for, they occur in these actions as Lagrange multipliers, which gives you certain constraints on the geometry. So from that point of view, they are well defined. Now what I want to do, and my talk is give you an example of new theory in gravity in 3 dimensions, which I call extended Barton gravity. Now we'll discuss it in a minute. Other things you can do is high spin extensions. So I discuss now some gaugings of spin 2 algebras, but in 3 dimensions in particular, people also have introduced algebras with, let's say, spin 3 extensions or spin 4 extensions of these algebras, and everything I said today can also be done for these high spin extensions. You can get them also for contractions of the relativistic case, and we recently completed a paper where we show, for instance, how spin 3 can be added in 3 dimensions in the non-relativistic case. And the funny thing is that while we were putting on the internet, there was a paper by these people here who have a paper about high spin states in a certain quantum Hall effect model. They call it the high spin magnetorotons. And well, maybe this work will have to do something with high spins, but I have not yet studied the paper in enough detail to see that. And I also told you that, for instance, you can also gauge other algebras, like the Schrödinger algebra, that gives you kind of non-relativistic version of the conformal algebra. And then you can apply this whole method of conformal tensor calculus as you know in the relativistic case. And for instance, then you can see that, for instance, you can use it also to construct things like Holographic gravity. So in some sense, Holographic gravity is nothing else than a high relative version of Newton-Cartan gravity. It's just, and then you have an action. So Newton-Cartan gravity, they are both based on the Schrödinger gravity, but just using different compensating multiplets. This gives a lower derivative thing without an action, and this gives you a higher derivative thing with an action, but they both have an underlying Newton-Cartan joint. But now, let me end this talk with showing how in 3 dimensions you can do something else than Newton-Cartan gravity. And I call it, because the point is that in 3 dimensions, you can, I told you the Bartman algebra is a central extension of the Galilei algebra, but in 3 dimensions you can add one more central extension. Because sometimes people associate with a spin. The first central extension associated with the mass with a spin, and that's called extended Bartman. And the reason that you can do that in 3 dimensions, an extra central extension, is that in 3 dimensions you can write the Poincare algebra slightly nicer because the space, the Lorentz rotations are in vector indexed in 3 dimensions. I can use the 3-dimensional epsilon symbol. And then to get the Bartman algebra with 2 extensions, you add 2 U1s, and then do this trick of contraction again, but now for 2 U1s, and then you end up with 2 central extensions here. And note this only works in 3 dimensions because I use here this epsilon symbol is the epsilon symbol of 2 spatial directions. So this algebra I write down here only works in 3 space-time dimensions. I mean, it's 2 spatial directions. But now I have 2. So the point is that in some sense 1 vector was good to cancel certain infinities in equations of motions. 2 vectors are even better, and now you can even cancel infinities which will arise in taking the limit of the Einstein limit action. And that's what you can do. So if you write in 3 dimensions, we know that gravity can be written as a Chern-Simons form. I've written it here. And now what you do is, before you take the limit, so it's not quite Einstein, I add this Chern-Simons term, containing the 2 vectors which belong to these 2 central extensions. So it's Einstein plus an extra term. And then I do the same contraction which I did before in the mass of Newton-Cartan limit, but I use now this sum and difference trick I use for both vectors. So I take here each time, it's not just a rescaling of the gauge fields, but I take sum and differences. And I use the trick for both vector fields. And if you do that, you collect all the factors of omega, then it turns out that all the infinities which otherwise would arise in this Einstein limit term can be cancelled by similar to infinities that arise if you take here the limit. And the whole thing is finite, and you get a Chern-Simons term. That's funny. It stops listening to me. Just a second.
Battery.
No, they're still that well. I can look like here. So you get now this action here, and in some sense this action is exactly the Chern-Simons theory of this extended Bartman algebra. And the nice thing of the extended Bartman algebra is that if you have a Galilei with 2 central extensions, it allows for this invariant non-degenerate bilinear form. That's why you can write down this Chern-Simons term. So you need the second central extension, which occurs here, to write down something with gauge invariant. And that's what we call extended Bartman gravity. And its equations of motions without matter, of course, are all curvatures are equal to 0. And in particular now the torsion constraint, the 0 torsion, is now also the equation of motion of this central, the vector associated with the second central extension. The nice thing of this theory is that if you compare it with Newton-Cartan gravity, you couple to matter, you get much nicer equations of motions. So if you couple in general Newton-Cartan gravity to matter, the problem is that only the matter occurs as a source term in the time component of the Ricci tensor. And since this was already strongly constrained by the Newton-Cartan equations of motions, you often get solutions with zero spatial curvature. So it's very difficult to make solutions of Newton-Cartan gravity in low dimensions with non-zero curvature. But here it turns out that is this new gravity theory that first of all the time component is sourced in a different way, and secondly all the other curvatures are also sourced. So it's much easier now to construct solutions with more general backgrounds, and that could be of interest for purposes of constructing, for instance, supersymmetric theories in a curved background. It's much easier to use the Festuccia-Cyber trick on this one to get supersymmetric solutions in a curve background than the other one. Now, why is it that, so you see now that you have two rather different looking non-relativistic gravity theories in 3 dimensions. Why is it now possible? Well, the difference is that you see, if you ask yourself, I call something gravity if it is inverted in the diffeomorphism and Galilei symmetries, then you have these two possibilities. But the second one is really possible because I also have this extra Yuan symmetry. So if you really ask, I only want Galilei symmetries, then it's only Newton-Cartan. If you allow extra Yuan symmetries and center extensions, then you get also more possible non-relativistic gravity theories. That's where the non-uniqueness comes from.
So
And
since you have just two special dimensions here,
What?
can one, since you have just two special dimensions, can one use the infinite dimensional conformal symmetries here?
You mean,
Because your space and time isn't.
this is, say it again, what's the question exactly?
So you have two-dimensional space.
Yeah, I have two-dimensional space, yeah.
So you can use infinite dimensional conformal symmetries here.
Yeah, well, for instance, you could, yeah, you mean in a similar sense that, for instance, the field symmetries arise in the boundary of an adhesive T, for instance, yeah.
Yeah. Or
Yeah, that in fact, yeah, that can be done, and in fact we did discuss this not for extended Bartman gravity, but we also in this paper we are writing, we did this for Carroll gravity and Galilei gravity in 3 dimensions, and then you do find that you can find infinite dimensional extensions of the Galilei algebra and the Carroll algebra. So I would expect here also that you get infinite dimensional extensions in that case, but we have not worked this out yet. But I would expect it, and that would be. Yeah. Let me see, I wanted to say something, I forgot what. Yeah, so what I want to say is that the non-uniqueness is based on the fact that they have extra Yuan symmetries. That's the extra new feature. Let me conclude by saying I have only 1 minute left. Is what I didn't discuss was supersymmetry, which was needed for the supersymmetric localization. It's funny that that people have supersymmetrized their activity, but so far in the literature, no supersymmetric extension has been given of Newton's Poisson equation. We did it in 3 dimensions, and in 4 dimensions, in principle, it's possible, but it just takes time, and if you don't know the answer, it's more complicated than you think. But I mentioned these several techniques, but I think the most promising one is now to do this null-reduction. Because I told you the null-reduction is a procedure to get from an answer in 4 by just doing null reduction for 5. Now certainly I can take also the supergravity in 5 and just do a null reduction. I don't think it's an algorithm, and just get what you get. And that looks like the most promising way to get the answer for the supersymmetric Poisson equation in 4 dimensions. And it is of some interest because what we found in 3 dimensions that if you find the answer in an arc frame, then if you gauge fix, it turns out that the Newton potential occurs in a non-trivial way. You also have to introduce a dual Newton potential, otherwise you can't realize the supersymmetry. And if you extend this argument to 4 dimensions, there are indications that you get, let's say, 4-dimensional Newton potential supergravity, but if you do gauge fixing, that you get kind of unconventional representations for the Newton potential. So somehow, to realize supersymmetry, you can't always work with the normal realization of the Newton potential. How it exactly goes, I don't know yet, but that's why it's still interesting, I think, to see how exactly now the supersymmetric extension of 4-dimensional Newton's Poisson equation goes. I'm almost there. So, yeah, the last thing I want to say, I didn't say much about the application in condensed matter, but as I said, many people from the condensed matter area are interested in coupling, not in the supersymmetric case, but in the bosonic case. And the reason is really that they are also interested not only in condensed matter model, they're also interested in geometric quantities like the Hall viscosity, and that has to do with response on pressure, and that is the same as coupling to gravity. That's why they really want to couple these effective field theories to Newton-Cartan gravity. And what happens then, because these effective field theories are high derivative theories, that it's not so easy to couple Newton-Cartan gravity to these high derivative theories. You get constraints. And these constraints are so severe that they get the relations between physical quantities. For instance, they derive relations between the Hall viscosity and the Hall conductivity. The conductivity is a response on the electromagnetic tensor. And they get really very explicit formulae by looking to this coupling to Newton-Cartan gravity. And it is very interesting, and that has led to all kinds of literature in the condensed matter community. And that has led to, as the last thing I want to say, is that we have come together as communities, and we are organizing together with mathematical physicists, high energy physicists, and condensed matter people we're organizing the very first workshop on applied Newton-Cartan geometry next year, March, at the Science Center in Stony Brook, to learn about each other's tricks and problems. So I would say save today, March 6 to 10, come on to Stony Brook, then we can talk more about the context of this seminar. And it's really interesting to see that the condensed matter people, for them, certain things they really don't know, which we know, and we don't know certain things they know. So there's really here an opportunity to have kind of very fruitful exchange of information. That's a nice way to conclude this seminar.
Thank you.